Hi, my name is Alexandru Dura and today I'm presenting the paper JavaDL, Automatically Incrementalizing Java Bug Pattern Detection. This is joint work together with Christoph Reichenbach and Emma Söderberg. JavaDL is a novel static bug checker framework for Java. It joins current state-of-the-practice tools such as SpotBugs and Error Prone. The current static bug checkers package a selection of detectors and provide an extension mechanism for users to write their own. Both the package detectors and the user-provided ones are written using an imperative language such as Java. To understand how JavaDL improves on the current state of the practice, let's have a look at the bug detector from SpotBugs. This detector is aimed at finding inefficient uses of the string constructor that take a string argument such as the one in the code snippet. Because string is an immutable class, using this constructor creates two heap objects that have the same content, thus wasting memory. This is how the detector implementation looks like. The code is concise and readable, but only if you're familiar with JVM bytecode, which is the intermediate representation on which SpotBugs operates. This style of implementation also mixes the what and the how of the analysis, which is fine if you only want to run the code. But what if you want to adapt the checks based on user feedback, for example, or avoid reanalyzing the entire code base for each change, or explain the generated bug reports? Essentially, this style of specification closes the detectors to analysis and transformation, so they behave like black boxes. But the literature shows us that we can do better. We have seen recent advances in alarm ranking based on user feedback, incremental computation, and provenance evaluation. What these advances have in common is Datalog, a declarative language that is more constrained but also more analyzable than Java. This enables us to build clear box static checkers open to architectural improvements. Then let's write the static checkers in Datalog. But we still need to figure out how to represent the analyzed program to Datalog. This is currently done using fact extractors or fact generators. In an analysis flow, such as the one shown here, which is inspired by the dupe points to analysis framework, we start with the Java sources, use the Java compiler to get the bytecode, then pass the bytecode through a fact extractor to get the fact database. Only then we run the analysis proper to produce the output. The problem with this setup is that the fact extractor is still a black box and the analysis are limited to what the intermediate representation can express. Our solution is to merge the fact extractor with the Datalog component and provide a language and a runtime where the analyzed programs are first-class facts and code fragments are used as predicates over them. Thus, we can go from Java sources to the analysis output in one step. To achieve this, we extend Datalog with syntactic patterns and semantic predicates. Now, let's have a look at the detector for inefficient string constructors implemented in JavaDL. In the first rule, we define the new string predicate, which states that in file F, line L, column C, we call the string constructor with precisely one argument of type tau. The first literal on the right-hand side is a syntactic pattern, which matches a new string expression, binds it to the variable n, and its single argument to v. Then we use a semantic predicate to connect v to its type tau. Finally, we use the source semantic predicate to retrieve the source location for the new expression. In the second rule, we define the string class predicate, which contains a single element, the declaration of the string class. In this pattern, the gaps match a sequence of declarations. Let's observe that built-in Java classes do not require special treatment in JavaDL. The last rule filters from the new string predicate the reports of interest. When we're done. This shows how we can implement the checker in Datalog extended with a very small set of features, syntactic patterns over the full Java language, and a small set of semantic predicates. In our earlier work, we have shown how to represent programs as Datalog facts and how to transform syntactic patterns to plain Datalog clauses. So now I'll explain why it wasn't straightforward to adapt the same techniques to Java. First, it's because Java is a much larger language than Datalog, and introducing meta-variables and gaps makes the grammar highly ambiguous. The syntactic pattern on the slide matches two syntactic categories: a method definition, if T is a type, or a constructor definition, if T is an access modifier. This required us to use an early parser to support ambiguity, and also to enhance the representation of syntactic patterns as plain Datalog, details that you can find in the paper. Once we represented the program as Datalog facts, we could write the entire analysis in Datalog. But Java type checking is undecidable, and Datalog is restricted to polynomial time problems. So we had to use the extend-j Java compiler to compute semantic predicates for name binding and the typing relation, which in Java are mutually dependent. To showcase the benefits of a clear box static checker, we implemented incremental evaluation with compilation unit granularity. That means that when a file changes, only the results derived from that file are recomputed. To this end, we implemented the meta-analysis, called domain separation signatures, that automatically splits the JavaDL program into local rules as the ones defining the new string and string class predicates in our previous example, and global rules, such as the one defining bad new string. The key idea is that the local rules are evaluated only for modified compilation units, while the global rules need to be evaluated for each run. You may have noticed on the previous slide that the type predicate is used in a local rule. But name binding and typing are not really local relations. To allow these predicates in local rules, which is critical to performance, we implemented a provenance tracking mechanism for semantic predicates by instrumenting extend-j's attribute evaluation. This was facilitated by the fact that extend-j is a compiler defined using attribute grammars. To illustrate how everything ticks, let's assume that JavaDL receives a set of modified files. The reality is slightly more complicated and is detailed in the paper. Based on this change set, the incremental driver looks up the files that contain semantic predicates which depend on one or more files from the change set. For this, the incremental driver consults the provenance database. Then it retracts the stale facts from the local relations and proceeds to compute fresh ones by invoking the extend-j compiler, which builds the abstract syntax trees for the files in the change set and for those indicated by the provenance information, which is updated in the process. Then, JavaDL represents the abstract syntax tree and the semantic attributes as local Datalog predicates and invokes the local Datalog program. The global program combines the output of the local program with the cached facts for the unaffected compilation units to produce the analysis output. Both the local and the global programs are evaluated using a modified version of the Soufflé Datalog engine. So far, we have shown that we can automatically incrementalize analysis written in JavaDL, but we still have to understand if JavaDL is a practical language for specifying static bug checkers. To this end, in our evaluation, we assess the expressiveness, the precision, and the performance of JavaDL. To compare with the state of the practice tools, we ported 10 commonly triggered checks, as reported in a recent study of static bug detectors. For all our comparisons, we ran JavaDL, Error Prone, and SpotBugs on projects from the Defects for J suite. For measuring the performance of incremental evaluation, we used a sequence of 500 consecutive non-empty commits from each project. Our first research question is how expressive JavaDL is. To assess this, we used the number of source code lines required to implement each check. We found that the JavaDL checks are on average 4.9 times more concise than their error-prone equivalents and 2.8 times more concise than their SpotBugs equivalents. While this is only a summary of our results, the paper contains a detailed analysis for each implemented static check. To measure agreement with the other tools, we use the notions of precision and recall, and we consider the reports produced by Error Prone or SpotBugs as the ground truth. The upper half of the table shows that JavaDL is able to reproduce the behavior of Error Prone to a high degree. For SpotBugs, JavaDL reproduces most of the ground truth reports, but it also produces many more reports. This difference is caused by the fact that SpotBugs operates on bytecode, while JavaDL operates on the AST and thus has access to all the source level information. In this plot, we display the average running times for JavaDL over a range of 500 commits. The results for exhaustive and incremental runs are paired together. Incremental evaluation is able to halve the running time for 4 out of 10 benchmarks, while it also produces some degradation for 2 of them. We observed that these 2 benchmarks contain a higher number of refactoring commits, which touch many files and force JavaDL to rerun the local program for virtually all the files in the project. To compare the running times of JavaDL and Error Prone, we configured Error Prone to run only the checks that we also ported to JavaDL. Error Prone and SpotBugs do not support incremental evaluation. In the plot, the gray bars represent the running times averaged over the commit range. We observed that, while JavaDL outperforms Error Prone only for 3 benchmarks, it remains competitive for the rest. The results for SpotBugs are similar and are available in the paper. In summary, we have shown how the JavaDL language enables the development of clearbox static checkers, which are open to architectural innovation. We introduced the JavaDL language, which extends Datalog with syntactic patterns and semantic predicates, and provides a runtime that supports both exhaustive and incremental evaluation. We have also shown that the JavaDL language is expressive enough to implement common static checks. It produces precise reports and has a competitive performance. We have published the source code and the artifacts under an open source license. This concludes my talk, and I would like to thank you for your attention.